I went to UW-Madison for college in the late 80s, and I started in the aerospace engineering program. And it was really short-lived because once I figured out that the curriculum, the it required the math courses, it was just astronomical on what I had to study with math. So I decided to move from space to another interest of mine is water, and got my degrees in hydraulic engineering. And I've worked for the Corps of Engineers since 1995. And this presentation is not a Corps of Engineers study. It's not put forward by the Corps at all. It came from a hydrology course that I taught a couple of years ago. And I want to thank Professor McDonald of Western Illinois University for coming to me and asking me to give this speech. It's really an adaptation of the astrohydrology that I finished my course with back then. And there's really been great discoveries in space in the last 15 years, and you may not realize how important that is for discovery of water. So I'll be showing that here. Here's my screen here. All right. So now, when I learned about water in space, they told me it wasn't there. And I was quite young back then, but I'm showing my age anyway by showing 1980. And they said the only place that water exists on Earth is here on Earth, and that is false. And that the cosmos is contracting and one day will collapse upon itself, and that's false. And the fastest speed of light uh, is the speed of light, and that's has a constant value, and both of those are false. And the only place life exists is here on Earth, and that's true so far, but we're still searching. And kind of proof of that is 4 spacecraft out there have recordings on them carrying a message from humanity to the cosmos in hope of finding extraterrestrial life. 1980, I was told the moons, the number of moons are right here, and you can see that we've discovered quite a bit. In Jupiter, from 15 moons to 79, Saturn, 11 moons to 82. Pluto, we could only see 1 back then, and now we've found 5. So the lessons that I took from that is that science changes over time, even a short time like 40 years. It's disputable and sometimes wrong. We have to keep on pushing to investigate and learn more, challenge our assumptions, and be humble, and admit when we're wrong and take that as a learning opportunity and not just push back against it. I'll be using this slide a little bit throughout the presentation today so you get an idea of the relative size of the moons and the planets that you see. And we're going to be searching for water in our solar system. Sometimes we find obstacles. Now there's different types of ice. We're looking for drinkable water, of course, but the temperature extremes are so dramatic that what looks like ice might be something completely different. There's saltwater ice, there's dry ice, ammonium ice, methane ice. And when we're also looking for signs of water, we're going to be looking at features like fissures, lava flow, water flow on the surface. That's really what we're looking for. It's hard to find in extreme temperatures that are out there. And then there's other fluid flows like liquid nitrogen flowing on Pluto. So I'm going to start in the logical order, start from Mercury and continue on out to Pluto and a little bit beyond. Now, with the different sizes of these planets come different gravity. So we're used to thinking of 32.2 for our gravity for Earth, but it really depends on where you're at. This particular slide shows that gravity isn't a constant value. It's slightly stronger and sometimes weaker depending on where you're at. And the assumption might be that in the mountain areas where it's really dense, you might get the highest gravity constant, but really one of the lowest constants is right here, closer to the equator. That has to do with the rotation speed of the planet. Here's some of the differences that might exist. So if we have a project, say in Puerto Rico, it might have a little bit different gravitational constant than 32.2, but this is primarily what we tend to use. So a table like this would be handy if you're going to do any kind of modeling on another planet or moon. You would use these different gravity constants here. And again, they're likely not constant. So let's start with Mercury now. I just wanted to show with this slide that the temperatures are really different. The backside of Mercury minus 290, and the front side is 800. And then space negative 455. So that might make you feel a little bit better about the temperatures outside right now. It used to be thought that the orbit was synchronous with Mercury always facing the sun, which would lead to a belt across the middle that might have a temperature between 800 and minus 290, like could sustain water. But it's since been found that there's a slow rotation and that belt wouldn't be there. So the only place that we've seen ice is at the poles. And here's a view of the North Pole, and ice tends to be in the craters, because if it's not in the crater, it gets cooked at 800 degrees, or definitely enough to evaporate or sublimate the water. Now here's a feature. This is a lava flow, and there's ways to tell if the braided channel that you see is lava or if it's water or some other material. And we'll get into that a little bit later. And here's a nice one, just for fun, Mickey Mouse pattern on Mercury. All right, so now we'll move to Venus. Okay, so here are these cloud formations, 1974. They've got much improved technology since then with the spacecraft, so they can use some penetrating instrumentation. And you can see in this photograph, you now see a lot of fissures and lava flows. Now to look at the temperature on the surface, the 872 degrees, it's higher than Mercury's because of the thick atmosphere, and then very cold again out in space. Now between the surface and the space, it doesn't just drop off instantaneously. there's a gradient, and it was found very recently, like within the last 2 or 3 years, that somewhere in that band, there's some floating particles that really got scientists excited about studying that. And so there might be a Venus project coming up soon to go investigate again. Now, if we look at the middle portion, you see lava flows coming out. And once again, some braided channels that are actually lava. Right, now this is lava, but it's not Venus. This is Earth. And you can see that the lava flows are oftentimes at a higher slope. It's a steep slope that influences the way the channels can braid. The material that's flowing is a different density, so that has something to do with it. The bed shear equation here, you can see the different factors. So gravity is going to be different than we're used to. If there's hardly any gravity, then it wouldn't flow downhill at all. So it's sinuosity. This is a simple calculation of how you can quantify a sinuous channel. So it's always greater than 1. If it's a value of 1.0, that would be a straight channel. Here's some types of channels right here. Okay, so on Earth with water channels, we see these wide meandering streams, and they tend to push themselves downstream. So over time, you will see different oxbows develop, and it moves downstream. So that's something that we would want to look for in other planets and moons. Here's a view of the types of sinuosity that you see in Hawaii. And if we go to Earth's moon, we see some sinuous channels here. And you can see how it's almost elevated, and it's flatter on top. So all of the sinuous channels on the moon have been found to be lava flows. But once again, at the poles, just like Mercury, there's been ice confirmed. And then when you say, well, what kind of ice is that? It does turn out that some of that is water ice. So might be locations for future stations to be built. Now, out at Mars, there's also the polar ice, the polar caps. The temperatures look not as bad as what you might think. At 70 degrees, that sounds pretty good right now. At the average temp of -80 and a minimum -220, there's actually a thin layer of atmosphere. It's carbon dioxide primarily, and that leads to carbon dioxide ice in most of the craters, and that's dry ice. So dry ice likes to sublimate. It doesn't become liquid. It just jumps right to gaseous. So when you look at these rims, and you don't really see the indicators of flowing liquid that you will in photos to come. Mars is the most observed and studied planet. Here's one. The Odyssey has been mapping the surface ever since. It's completely mapped. And if you haven't explored your Google Earth much, there's a button at the top of Google Earth that has a little icon that looks like Saturn. And it's got Mars and Moon on there. I won't do a live presentation with Google Earth because it's a bandwidth hog. But here's what Mars looks like. So instead of Google Earth, I call it Google Mars. And the point of location, the feature in the center here, is a good reference point. It's called Olympus Mons, or Mount Olympus. It's 3 times the height of Mount Everest. It's the largest volcanic feature in our solar system. Going to the northeast, there's some sinuosity that you can find on Google Mars. And just like on the moon, you see a lot of these sinuous channels look like they're elevated and they're flat when it flows out here. So those are lava flows. Now here are some other output from different places on Mars. And this one here, the name of it kind of gives it away, aqueous. Okay, these are more sand dunes because there's wind on Mars. But if we go to aqueous, and sorry about that, we look and see this looks like a braided channel that might be water. If this was lava, it wouldn't be pushing up a carved channel up this way. This is more of a tributary channel, and it just looks like the braiding would be water. Plus, they named it aqueous. Here's another look of a different channel where you see these lines. At first, when I looked at this, I thought it was a HEC RAS model with these different lines, but these are sand dunes in a pattern that's different than what we would see on Earth, perhaps. But with the different gravity and temperature extremes, there might be differences like that. And this could be something that could be modeled with a sediment model to see if these bed forms could be produced with flowing water. But another indicator that these aren't just blown wind dunes is that the wind would also occur up on the flats, and there's no similar structures up here. There's no sand dunes like down here. So this is likely to be a past waterborne channel. Now this is a water of the present. This is an amazing slide, amazing photo. The rover was right there in 2015 taking a shot of this with seeping liquid coming out of a crater rim. And these dark streaks here are flowing water, and only in the sunlight because it'll freeze at night. Here's a different location, and you see those streaks as well coming down here. So this would be more of a channel way. I just thought this looks like a really good place for a ski resort. Ski hills here, another one of my hobbies. And subsurface oceans. There was theorized to be one, but with more observation with ground penetrating density meters and other technology, they found that there's 3 large oceans under Mars that could be tapped into, perhaps. So now we'll move out further in the solar system. We'll go to the asteroid belt. Now, this looks very dense, and there's over 1 million asteroids. but they're not crashing into each other like the movies show. They're really quite far spaced apart. But there's really two very large ones that are significant that make up about 45% of the total mass of asteroids. And one of those is Ceres, and the other one is smaller. It's called Vesta. So let's go to Ceres. Ceres is about the size of Florida. When you compare it to the other sizes of planets, you got Mars and Mercury here, and our moon just a little bit smaller than Mercury. Ceres is quite a bit smaller than our moon, but it has enough mass to crush itself into a relatively spherical body, and that's why it can be categorized as a dwarf planet, where Vesta does not have that kind of mass. It looks more like a potato shaped, um, so it's not considered a dwarf planet, but it is the largest asteroid in the asteroid field. Here's a remarkable picture Ceres. This was in 2015, and the distance is 29,000 miles. Now, we had to wait over 3 years to figure out what this shiny thing was in the crater. So there was a lot of speculation about that. And unfortunately, it wasn't a water ocean like what people were thinking. But 3.25 years later, the Dawn spacecraft got there, 2018. And here's a view of the largest of the shiny. So it looks like crystals, looks salt. It is salt flats. When you look at the rim, there's actually runoff of flowing. So there is a flowing liquid, salt, coming over the rim of this dwarf planet crater. And with density estimates, they figure there is a lot of water ice layers underneath this, smaller than our moon body out there. So we're going to move on to the gas giants. The dwarf planet, the Ceres, would be one of these smaller ones here, dots. And you got these two, Uranus and Neptune, have been renamed as ice giants. And Jupiter, Saturn are gas giants. And then here's Earth. Okay, Jupiter. It's got 79 moons. It has rings. Nine spacecraft have visited it, although 8 of the 9 have just flown by, and only Juno has stayed to explore. So with the planet itself, there's some neat formations. At the North Pole, there's these cyclones, number of them. I think there's 8 in this photo. With X-ray technology, um, they've detected these auroras, and there's lightning, which indicates that there's probably water clouds in the atmosphere that could help generate that. Great spot. There's been some studies on that, on how there's like a mini atmosphere generating winds 400 miles an hour, so more than 2 times faster than our fastest hurricanes. And then studies on the inside. And this liquid metallic hydrogen is something new that they say could be used as a future rocket propellant, although trying to extract it from here would be impossible. But there's some of this detected on Earth as well. Now here's the explorer who discovered the moons on Jupiter, 4 moons. He had a 20 power telescope, which today you should be able to find quite readily. And if you've ever looked through a telescope and seen these and the stripes on Jupiter with your own eyes, it's really amazing. Here's some sizes. I've placed some little indicators of which ones are which. J1, so that's the first moon on Jupiter of the 4. So it goes Io, Europa, Ganymede, and Callisto. And those are here. Those are the largest moons, so they get the most attention. And it's about, the first one here, Io, is about the same size as Earth's moon, but these two are larger. Here's some quick photos and facts. More than 400 active volcanoes. The temperature is so hot here, mainly from friction being close to the planet Jupiter. So, finding water there is difficult. Now, Europa is the second one. There's lots of fissures and cracks, and it's estimated that subsurface salt water up to 2 times the volume of all of our oceans on Earth. So this really captures the interest of scientists, and there's a project going on right now, this Europa Clipper. They're planning to launch it in 2024, and it would arrive in 2030. The third moon, Ganymede, it's larger than Mercury, has a magnetic field, so that tells you about what the core of the planet might be, and it might have water as well. So there's the core, the iron core, that creates the magnetic field. There's these different types of ice, hexagonal and tetragonal ice, saltwater, ocean, and a map here. Location shown on the map. Now this one is heavily cratered and also has potential subsurface oceans like Ganymede, but it's not currently studied. Okay, we go out to Saturn, 82 moons. Cassini spacecraft was there for 13 years studying the Saturn system. It took some amazing pictures like these. At the North Pole of Saturn, there's a hexagonal area. It looks like it's almost unnatural that something would form in a hex like that. And then using the cloud penetrating technology, there's these various little cyclones and counter cyclones in here. Now the rings are probably the biggest surprise, is that 90 to 95% of the rings of Saturn are not only ice, but water ice. That's why they're so reflective. Compared to the rings on Jupiter, which aren't as reflective, those are more rocky rings. These rings on Saturn really have a lot of potential, and you can see there's little small moons that are inside of them as well. Now, when you see this slide, you might have thought this was Saturn to begin with, but that's really a moon, and that's Titan. Saturn is this line down here. Thank you. Titan is the largest moon of Saturn. You see this blue line here, that indicates that Titan has an atmosphere. Makes it besides its size, a real place of interest. These other ones have interest as well. Like this moon, Rhea, has it has oxygen. It's not enough for us to actually breathe on, but but for there to be an atmosphere with oxygen is amazing. This one here, Enceladus, that one is important as well with water findings. Let me move on to Titan. Now, Titan has some features through the clouds down below, and that was suspected that it would be oceans, lakes of liquid methane. So this lander was launched from the Cassini spacecraft. I don't know how to pronounce that. The lander, HUIGENs, came down. It took pictures on its way down. This right photo are pictures of the mountains and valleys. There's a map here of the various bodies of water. Well, not water. So these would be methane and ethane seas. So the methane has to come from somewhere. Actually, as a building block of life, um, as one of the indicators, but it's not the sole source where methane could come from. So underneath this methane and ethane is the water ice and water that we're looking for, because water is more dense. So if you threw an ice cube into a lake of liquid methane ethane, it would sink. So that water ice would be down here. And here's a diagram that would show what we might find if we drill. This project is amazing. It's currently in the conceptual design phase by NASA, and it's a submarine. And the plan would be in the late 2030s and early 40s to send this submarine to probably the biggest lake on Titan and explore it. Here's a different moon, this Enceladus. It's easy to remember because it sounds like enchiladas. I like those. I can't forget the name. This image is really nice. It's got the ridges. It's nice definition, 2015. And there's a lot of water in oceans underneath of here. And as the spacecraft was coming by, there were large geysers of water spraying up into space that it was detecting. And there's a smaller moon, almost identical, called Dio. Saturn's moon Mimas is mostly made of water ice, so it's like a giant snowball in space. Uh, Here's something. It's got the gigantic crater on it, and someone put this together. I just couldn't help but show this that Saturn's moon Mimas looks totally like the Death Star. Oops. All right. So I said before that these are ice giants, and that's because the cores of these planets are different than the cores of Jupiter and Saturn. Uh, right? Jupiter and Saturn, they're mainly hydrogen and helium um, mantles of metallic hydrogen. These ones have rock and ice at, at the middle. Planet Uranus orbits the sun like a spiral thrown football, different than all the other planets. So that's an indicator it might have had quite a catastrophe in its history. That something hit it and it rotated from its original spin. Here's a look at the rings and various moons in the rings. So the inner moons are roughly half water ice and half rock. That's amazing discovery for a planet that really hasn't had very much exploration compared to others. And Neptune has had very little as well. Neptune, it has rings, very faint, and great spots appear and they disappear. That's still under their exploration. Scientists are looking at that. 2018, this big spot appeared. Here's a look at what the middle might look like. What it's composed of, rock and ice. Now, the largest moon, Triton, there's plans to explore that. So, based on Hubble measurements and other space telescopes, there's more space telescopes than just Hubble. Hubble gets the credit for most of it, though. I think there's four primary ones. But this image is from NASA. So below the icy shell would be possible ocean, and there are geysers that are observed coming out. So Triton is this size compared to Earth. You can see that it's just about the same size as our moon, and it's a little bit bigger than Pluto. So we're going to go to Pluto next. Pluto fairly recently discovered it has 5 moons. The large one was visible a long time back, and it's a significant size as to Pluto to where they actually orbit around each other in a binary way. They found that there's underground oceans that are likely to be liquid water on Pluto, and there's enough friction between these two rotating to keep the interior warm. Here's an amazing photo, 2015 New Horizons spacecraft showing hill-sized icebergs that are water ice, and they're floating in a sea of frozen nitrogen. Now, if it was liquid nitrogen, they would really be floating, and it'd be different, but it is so cold that it's frozen nitrogen, and it's more of a glacial flow. And here's a cross-section cut through it. So showing these little icebergs here are water ice. And then below you get this ocean, liquid ocean uplift. Now, this crust doesn't crack and just fall down because there's not very much gravity there compared to Earth. So that's one way that this would be under pressure, but not so much that it's erupting geysers out from underneath like other moons are doing. Okay, so we're getting close to the end of the solar system, but there is more and much more beyond Pluto. Here's a view of the various dwarf planets that have been discovered beyond Pluto. See, one of the first ones that I heard of was this Sedna. But then this is the real biggie right here, Eris. When it was discovered in about 2005 time frame, it's actually larger than Pluto. Then scientists have to say, well, are all these things planets or not? Because this one is larger than Pluto. So in 2006, they decided to come up with a new term and definition for dwarf planet. And that's what took Pluto away from planet status. And it's considered dwarf planet now. So the three things were that it has to be heavy enough to be more of a spherical body, which this one over here, Haumea, does not look spherical. So I don't know how that gets away with dwarf planet. So spherical shape, clearing the orbit of all other debris and asteroids is another parameter for a full planet. So the dwarf planet Ceres doesn't do that in the asteroid belt, so it can't be a full planet. Then the way that its orbit is around the sun, it's got to be on a plane, and Pluto comes in at a different angle, so another disqualifier. So in 1980, just thinking up there in the in, in the solar system, is there any water up there? And I was just saying there might be, but they told me that there's not. But now in 2022, you got to say there's water everywhere. Where isn't there water? And it's time to go and have a drink. That concludes my presentation on waters in space. And if there's
All right, fantastic job.
Right.
It's time to have a drink. Might be a little early,
Yeah.
but it's time. No, thank you. Fantastic. I think Brad will monitor the chat if there's any questions. Definitely great presentation. Well done. Pluto will always be just a planet to me though, so I can't recognize it as a dwarf planet. It'll always be right.
Yeah, there's some stubborn ones. That's true.
You said something when you kicked it off. You said learn more, challenge our assumptions, and be humble. I think that's very sage advice. Um, and then also, I agree with you. I too like Enceladus, so I think I'll probably dig into that a little bit further as well. So, but we wanted to open it up. Appreciate everybody jumping on the call. Wanted to open it up for any questions for Tom. Certainly a very interesting presentation.
Oh, thank you.
Brad, you see any questions out there, or it was just
That not yet. I guess.
Okay.
I guess I would ask Tom what NASA projects he's most excited about in the near term. Tom, do you have any thoughts on?
Yeah, I'm thinking, I mean, that submarine project is pretty neat, but it's not exactly near term. The time frame of doing these projects is even longer than, some of the biggest government projects that I've seen. This Europa Clipper is probably the favorite near-term project. There's so much water ice to be had in Saturn that if this ring is mostly water ice, then we don't really need a station on a moon to get the water. We can just harvest it from there if we had people out there working on various future, distant future projects. And two, there's really not going to be that many astronauts out there doing this to where they need a whole lot of water. And let me show you the size of those rings again. Let's see. Where is conception? There it is. So if you just look at how big this ring is compared to our planet, that's amazing. But Europa is one that's going to be investigated and landed upon. The Titan one is interesting, but I don't know that I'd want to be in a methane environment like that. On the surface, there's reports that it rains, that it has weather patterns, and it rains liquid methane and ethane from the cloud systems there. But then when I read that it's habitable, I think, well, that's not quite the habitat I'm looking for. And I do find space to be very therapeutic. It gets you away from it all. All you have to do is look up and you see different formations up there, constellations. Really helps with stress relief, and it spurs on your imagination too, which we can use in our current projects.
Thanks, Tom. And you said you actually taught this as part of your hydrology class at Western. Is that correct?
Yeah, I did. It was the final class. I thought what I would do is give them an idea of how hydrology concepts could be applied in space. And I showed them the braided channels and talked about slope and how to distinguish from photos the difference between a lava flow and a and water flow. And that motivation for them to reach for the stars, as I was saying goodbye to them for the semester.
And how did Professor McDonald, was he sitting in on your class then? Is that how he found out about
Yeah,
it?
he was sitting in on that, and he really liked it, and he wanted me to give that presentation again sometime. And so I did that once with him, and he had his family there watching, and they thought it was a great overview. Now this one at this conference is a 45-minute time block, so I really only had about 20 minutes. So by coming to ASCE today, I had a chance to go in and fill in a lot more of what what I was interested in, and now I've got more of a complete look at waters and space of the whole solar system. So that's been helpful.
Excellent. Yeah, and we'll have the recording for you too, in case you want to extend it out to Professor McDonald again.
Yeah, I will. That's great. Thank you.
We'll wait another minute if anybody has any questions. But in the meantime, Tom, really appreciate your time today. Very informative presentation. Um, like Brad said, we will have will be recorded, and they'll more than likely be uploaded to the Rock Island's website eventually. So feel free to reach out to Tom as well. You have his bio and his email address if you have some other questions for him. But thank you, Tom. Appreciate your time today. Thank you, everybody, for jumping on the call, and have a great weekend.
Thank you.
Great job.